How we walk is an inherent part of how we present ourselves. Gender, job, style, age, different aspects of who we are reflected in our walking pattern. For example, models adjust their walking pattern to look cool, sexy, and fashionable. Yet, no matter what we want our walking to express, for all of us it remains crucial to consider our energetic cost and stability. Yes, you heard that right. I said crucial. Even though you might not actively consider it, energy and stability demands determine how you walk. By changing the way we walk, we studied the energy cost of walking stability. Let's give an example. Older adults walk with a higher energy cost compared to young adults. The question is whether this higher energy cost in older adults is related to their stability during walking. To answer this question, we need to know what determines the cost of walking in young and older adults. Young adults spend almost 60% of their total energy cost to generate propulsive force and to propagate their leg. Do they need to spend part of their energy cost to control their stability during walking as well? People study this. There are actually several papers about energy cost of walking stability. In these studies, they use gas analyzer to measure energy cost of walking. They also use external lateral stabilization, which is a spring-like construction. During walking with external lateral stabilization, two springs pull the subjects bilaterally to provide more stable walking pattern and subsequently to reduce energy cost of walking. However, these studies reported inconsistent results. For example, Donnellan et al. Showed a significant reduction in energy cost during stabilized walking at both preferred and zero step width conditions. However, Dean et al. Found a significant reduction in energy cost during stabilized walking only at zero step width condition. In our most recent study, we also didn't find a decrease in energy cost in stabilized walking. We tried to understand why these results are inconsistent. For this, we did a systematic review on all of these studies, and we found that these inconsistent results could be due to differences in walking conditions between these studies. For example, walking at preferred or zero step width, walking with or without arm swing, or differences could be due to differences in habituation time or in stabilized devices between these studies, such as differences in spring stiffness or in rope lengths used to attach bilateral springs to the participants. So, to better understand the effect of external lateral stabilization on energy cost, we also did a meta-analysis on individual participant data from these studies. In our meta-analysis, we took the aforementioned differences in walking conditions and stabilization devices between these studies into account. In our meta-analysis, we considered those studies which included a group of healthy young adults participants. We found 7 studies from 4 different laboratories reporting on a total of 92 participants, and we requested the individual participant data from these studies. We performed multi-level analysis on the data to investigate whether step width, arm swing, rope length, spring stiffness, and habituation time affect the difference in energy cost between walking with and without external lateral stabilization. Our meta-analysis showed a significant reduction in energy cost only during stabilized walking at zero step width and without arm swing. This means that if you walk normally, you need only a small proportion of total energy cost to control your medio-lateral stability. But if you walk at zero step width and without arm swing, this proportion is larger. This brings us to the question, why we need more energy to control our stability during zero step with and without arm swing. During walking at zero step with, foot placement is constrained. Therefore, other stabilizing strategies such as frontal plane ankle or hip movements will be needed, and these strategies are energetically costly. Moreover, arm swing plays a stabilizing role during walking, and this role can become more important when participants have to walk at zero step width. Therefore, due to constrained foot placement and absence of arm swing, maintaining stability becomes more challenging, which may lead to increased energetic cost for control of medio-lateral stability. We also found that if short ropes are used to connect the bilateral springs to the participants, energy cost reduction can increase, because spring fixed in AP direction may provide unwanted assistance in the anterior direction and assist the propulsive force generated by the participants. And these potential unwanted effects may increase by using short ropes to connect the springs to the participants. Our meta-analysis also showed that spring stiffness and habituation time did not affect the energy cost reduction due to walking with external lateral stabilization. Based on the results of our study, we can conclude that young adults spend a small part of their energy cost to control medio-lateral stability during normal walking. But if they walk at zero step with and without arm swing, they need around 10% of their total energy cost for this. Moreover, due to potential effect of rope length on energy cost reduction, future lateral stabilization studies are recommended to use long rope length or trolleys to prevent slacking. Future lateral stabilization studies are also recommended to select a spring stiffness between 760 and 2200 Newton per meter, and to apply a habituation time between 0 and 7.5 minutes. And at the end, we would like to thank those researchers of lateral stabilization studies for providing us their data, which allowed us to perform an interesting meta-analysis.